Good morning, AP Chemistry. This is Chapter 7, Section 1. This is Atomic Structure and Periodicity. We are going to go through electromagnetic radiation, Bohr model, and then we will go on to quantum mechanics, quantum numbers, and trends of the periodic table. And all of this you had first year chemistry, so it is really just a review. So the first part we're going to do is electromagnetic radiation, EM for short, which basically stands for all light. Any light, radio waves, microwaves, gamma, X-rays, all forms of light, radiant heat, all that kind of stuff, electromagnetic radiation. Look at that. Electromagnetic radiation. Electromagnetic radiation, EM for short, and if you ever watch any science fiction shows, they're always talking about the EM field, is energy that travels through space by electromagnetic radiation. So it is light, aka energy. Sunlight, X-rays, gamma rays, fireplaces give off heat. Once scientists thought light was pure energy. It had no mass, it had no matter properties, and they thought matter had no light properties, no wave properties. They thought that light, aka energy, and matter, particulate matter, were two separate entities, and they had no commonality between them at all. So that's what they once thought, and these guys coming up were the guys who threw it all out. But first, energy, aka light, has a couple of properties we have to discuss. All right, we're going to go through energy first, and we're going to do some properties of energy. And there are three properties of energy. Two of them you absolutely have to know. The third one is just a definition. So waves, which is of course energy, and it comes under the electromagnetic spectrum category. Wavelength and amplitude. Of the two, wavelength is more important. You're going to have to know wavelength and frequency. We will discuss frequency in a minute. Wavelength is the distance between identical points on successive waves. Easiest to measure it from peak to peak. So for example, just like it shows, this spot and the identical spot on the successive wave on the next wave, and the symbol is this Greek symbol, what I call an upside down Y, but I believe the Greeks call it the nu symbol. It is the distance between identical points on successive waves. You will be calculating and measuring waves in either meters or more frequently nanometers. So wavelength with this symbol is really important. Amplitude is just a definition. It's basically the height of the wave, but the height of the wave is measured from the midline to the height of the peak or the trough. Notice on this picture here, this is the amplitude, not this. That is not right. This is the amplitude. This is the amplitude. This is the amplitude. Also, the crest, so it is the height, and the trough sounds just like horse trough for a reason, and it is the lowest point. So this is the highest point, and this is the lowest. Frequency is the other most important property of a wave. Frequency is exactly like it sounds. It is the number of waves that pass through a particular point in 1 second. The units for frequency are going to be varied. They're going to mean the same thing, but there's a couple of different ways to write them. And the units for frequency are hertz or per second, which I'll write 1 per second if you like, or second to the -1. The symbol for frequency is this guy. Again, I write it as a cursive V. This is also a Greek symbol. This symbol for frequency, and here is your wavelength symbol. Oops, that's a terrible wavelength symbol. And this is your wavelength symbol. So this is the symbol for frequency, not the units. And this is the wavelength symbol, not the units. All right? So those two are going to be exceedingly important. Wavelength. All right. There is a computation. All light travels at the same speed. The speed of the wave, and we don't use this symbol. It's a C, we call it C. Speed of light is wavelength times frequency. So I'm going to go through this a little bit. Wavelength, a property of a wave, the distance between two peaks. Symbol, units. Frequency, exactly what it sounds like. How frequent is your wave? Symbol, units. Speed of light, calculated by wavelength of light times its frequency. Notice that if you were to do it just in units, you would have nanometers per second. So the units for the speed of light are going to be nanometers per second, which is exactly what we're going to focus on. Symbol for speed of light is a C. Symbol for wavelength is this upside down Y. Symbol for frequency is this V, this cursive V. These are the symbols. These are the units. Maxwell proposed that visible light consists of electromagnetic waves. Electromagnetic radiation is the emission and transmission of energy in the form of electromagnetic waves. In other words, electromagnetic radiation are waves, are energy. The speed of light in a vacuum, you have two options. They are exactly the same quantity, they are different units. You can use 3.00 times 10 to the 8 meters per second, or 3.00 times 10 to the 17th nanometers per second. This one just converted from meters to nanometers. This is the one we're going to use most, and I'm warning you right now, your AP College Board usually writes it down as 2.9979 times 10 to the 8th and 2.9979 times 10 to the 17th. Don't panic. Use 3.00 because that's the easiest to remember. 2.9979, that's easy to remember too. It's going to give you the same answers. Just be aware that most of the literature rounds it up to 3.00, and for some reason the chemistry book, Zoomdall, and the AP College Board refers to it as 2.9979. Make sure you know the 7 parts of the electromagnetic radiation and in order of. At this end, this is the higher energy end. This is the higher frequency. This is the higher energy end. And this is the shorter wavelength end. There are 7 parts. From high energy to low energy, you have gamma, X-rays, ultraviolet or UV, visible light, which of course is the only part of the electromagnetic spectrum that's visible, infrared, microwave, and radio waves. At this end, the radio waves are the lower frequency. They are the lower energy, and they are the longer wavelengths. You have to be able to list them either from higher to lower energy or lower to higher energy. There are 7 parts. The only one that is visible to the naked eye is, of course, this part, which brings us down to our lovely colors here. Our Roy G. Biv, that's backwards. This is still the Roy G. Biv, but it's slightly backwards. Now again, every one of these electromagnetic spectrum, energy, or light, whatever you want to refer to it as, will travel at the same speed. Light travels at the same speed, 3.00 times 10 to the 8th meters per second, or 3.00 times 10 to the 17th nanometers per second. Every one of these has the same speed. All right, pertaining to just the visible light range. Again, as youngsters, you knew Roy G. Biv. And you remembered the colors, red, orange, yellow, green, blue, indigo, violet, as Roy G. Biv. The visible light range is just the reverse of Roy G. Biv. They have it, again, you're going to have to know this from high to low, low to high, whichever way I want it listed, you are going to have to know this. This is your high energy right here. This is the highest energy. This is the shortest wavelength. This end right here. This is the shortest wavelength, and this is the highest frequency. The red part is your lower energy, lowest energy, your lowest frequency, and your long wavelengths. Again, notice long wavelengths, 700 nanometers is longer than 400. You're going to have to be able to list it from either low energy to high or high energy to low. This is only one section of the electromagnetic radiation, and this is the only section of the entire electromagnetic radiation spectrum that I want you to know the wavelength ranges. It goes from 400 to 700 nanometers. Put that into your brains also. 400 being the violet and 700 being the red. So this is the only part of the electromagnetic radiation I want you to know the actual wavelengths of. The rest you will be able to look up. All right, let's do a little pictorial. You will notice, I'll number them, wave 1, wave 2. You will notice that wave 1 has a much longer wavelength. You will also notice that wave 1 in 1 second really only gets one peak, whereas wave 2 has about 10 of them. So wave 1 has smaller frequency, lower. And what we're going to discuss shortly is the energy of the wave, but if you look at it logically, each one of the two looks like it has a higher energy. To me, it's this one. This one's also going to have the higher energy, and this one's going to have the lower energy. All right, so make sure you can list visible light and the wavelengths. All right, here's an easy peasy example. Red colors seen in fireworks are due to the emission of light with wavelengths around 650 nanometers. Notice 3 sig figs. What is the frequency of red light with a wavelength of this magnitude? They are asking me what the frequency of this light is, how many peaks, how many waves in 1 second. The speed of light is equal to the wavelength times frequency. We are calculating frequency. So frequency is equal to the speed of light over wavelength. Now here's where you got to do a little thought. Which C am I going to use? Well, my wavelength is in nanometers, so I'm going to make my life easy, and I'm going to calculate the frequency using him. Plug it into your calculator, 3 sig figs, and the frequency is per second. Also can be written as hertz. Also can be written as seconds to the -1. What that means is in what this number means that in 1 second 4.62 times 10 to the 14th waves pass by. Lastly, the relationship between wavelength, there is the symbol for wavelength, again symbol, and units, and there is the symbol for frequency. That's the symbol. The units can be hertz per second, second to the -1. So the relationship between wavelength and frequency, and again a little picture here. Notice the relationship is inverse. It is an inverse relationship. The higher or longer the wavelength, this is number 1 here, this is the wavelength from peak to peak. The higher or longer the wavelength, the lower the frequency. You only get maybe 1 peak in a second. The lower or shorter the wavelength, on the second example, the higher the frequency. You're going to get a lot more peaks in this example than you did for this one. And that's everything for this video.